2 weeks ago, I talked about climate change, talked about scenarios of emissions, but I focused on how to do it, what its cost would be, and what sort of policy instruments the government has at its disposal. And this week, I'm going to talk about the impacts of climate change. I'm going to start today talking about the impacts in their physical and biological and human manifestation. And then tomorrow I'm going to talk about the impacts from an economic perspective. And in between, I'm going to do a bit of catch up. I'm going to assume that you did not take much environmental economics, or if you did, you didn't take much notice. So I'm going to review briefly the valuation, monetary valuation literature as well. Is that a wrong assumption? No. That's what I thought. So that is the game plan. And then tomorrow I'm going to talk about the economic impacts of climate change, statically, dynamically, at the margin, in total, and its relationships with developments, as well as its relationship with climate policy. And then next week I'm going to put the cost of greenhouse gas emissions and the impacts of climate change together in cost benefit analysis. So that is the plan. I talked about climate change. Has many impacts. The most obvious ones are on vegetation. So if you drive south through Europe, you would notice that vegetation changes. And part of that is soil. A lot of it is climate. Different plants grow in warmer conditions than in colder conditions, in drier conditions than in wetter conditions. That is obvious for if you look at individual plant species. Some do well, some don't do well if it's very hot. Plants also compete for resources. So it may be that a plant is well able to survive in a particular climate if it were on its own, but it may be unable to compete with other plants and may therefore disappear. Right? Same is true for animals. Some do better in hot conditions than others. And animals, of course, eat plants, so if their favorite food disappears, or the necessary food disappears, then the animals would follow. And what is true for herbivores, then automatically also get into the predators. Even if an animal may be fairly robust to the climate, even if it's not eating plant material at all, if its prey is disappearing, then of course that animal is in trouble too. So you would expect that if temperature is different, if precipitation is different, then vegetation would be very different as well. And let's look at the top map for now. What you're looking at here is not changes in individual species of plants, but changes in wholesale biomes. Biomes are essentially composites of plants and animals. The colors here mean white, no change. It's only about terrestrial vegetation, so the oceans are all white by construction. And then the darker the color, the more models disagree that something would change. The sort of changes that we're talking about are biome changes, that is, changes from savanna to forest, or from tundra to forest, or from forest to taiga, or something like that. It's not from one species of fur to another species of fur. No, it is wholesale changes in um, in the biome, and therefore um, in the way the entire landscape looks and feels. Um, you may wonder, so what, right? And you may wonder what to do with a vague prediction, like everything will be different. There's a few general rules that hold here. One is that specialized species tend to fare much worse on the conditions of change than generalist species do. And one example of that is edelweiss. Um, I think of as a song by Lady Gaga, but it's also a plant that lives high up in the Alps. Um, High up in the mountain is actually a pretty harsh environment for plants. Very sharp temperature differences, can be very hot at day, can be very cold at night, can be very cold there, very dry there, sorry. And there's a lot of radiation because there's less atmosphere to protect yourself from that radiation. Now, Edelweiss doesn't particularly like it up there, but it is sort of the only plant that can survive up there. And other plants would simply not make it through the year in the conditions that you see there. I mean, a whole lot of people here grow Edelweiss in their gardens, and it's perfectly happy there, provided that you protect it from its competitors. You need to weed very vigorously because it would be quickly overwhelmed. So now what happens to Edelweiss if climate changes? Make it too hot up there, so the logical response for a plant like Edelweiss is to move north. But if you live on a mountaintop, then the way north is not the small step, but it's the next mountaintop north. So that would mean that the plant has to travel through the valley up the next mountain, which is difficult because there are all the competitor species that take away its warm light and what have you. So that may not really be an option. It may be that the wind could blow seeds to the next mountaintop north. But then if we look at the geography of the Alps, at the northern edge of the Alps, the next mountain range is all the way in Norway. So there's no way that a plant can make it that distance in a single leap. And that implies that for a plant like Edelweiss, climate change would simply wipe away its ecological needs, and it would go probably locally extinct. It's such an iconic plant that it will be preserved in botanic gardens and probably in people's gardens as well. But in the wild, it would be in trouble. So that is what I mean with a specialist. Specialists are sort of like geared toward working on a very, very particular environment. They're the only ones who can do it if that environment changes there and forth. The species that live larger would also see very large changes. So at the moment they're clinging onto the margin of their ecological niche. They essentially survival if things may just be in deep, deep trouble. Or it may be that actually their ecological niche expands from the margin to what is coming. Right? So species that are currently marginalized would either disappear or become much more common. So those are the sort of wholesale changes that you would expect. Going back to the question, so what, right? Why do we care about these things? If you look at how people actually value nature, it is not from coming across things they see every day. It's not the generalists that we value. People rarely get excited by seeing more grass, right? Because it's everywhere, or seeing, definitely if you're from Europe, like Douglas firs or things like that. Those are very common species. People get excited when they meet uncommon things. And it's the uncommon things that will be most in trouble because of climate change. Now, that is natural vegetation. The same principles of all change also hold for managed vegetation, the stuff that is going on farms, agriculture. What you're looking at here is 6 graphs for maize at the top, wheat in the middle, and rice at the bottom. These are essentially what feeds mankind, humankind. These are the 3 main staple crops. A large share of the calories that we get come from these 3 grains. And then at the left, you're looking at what's happening in temperate regions where we are. At the left, you would look at temperate regions, and at the right, you're looking at what would go on in tropical regions. And then the horizontal axis are scenarios of climate change. The vertical axis are changes in crop yields. The dots are primary estimates. This is what single studies have said would happen to the yield of rice in Vietnam, right? That's what a single dot would represent for a 2-degree warming, say. The curves that you see drawn are sort of the best fit to this diversity of studies. What you see is a bit of a confusing picture. You see positives, you see negatives. Overall, the tendency is that more pronounced warming would be more negative. You see a sharp decline for wheat, a much more gentle decline for rice. That's no surprise. Wheat is a cold-loving plant, rice is a heat-loving plant. You also see, and I'll get back to that at length, a difference between the reds and the blues. And I haven't explained to you what the difference in red and blue. In red, we assume that farmers just keep doing what they've always done. They keep planting the same cultivars at the same time, keep applying the same fertilizers and the same pesticides, and they keep harvesting at the same time as they have always done. Or rather, as they're currently doing, because they haven't always done this. Right? Farming practices have changed quite radically over the last 10,000 years and even over the last 10 years. Go ahead. You think I'm going to answer that question? You would indeed expect, as you very rightly noticed, that what happens here with adaptation is that if you change cultivar, you change your planting date, you change your harvesting regime or your pesticide regime, then you would expect a smaller change at the very least. And you see that, for instance, for wheat in the tropics, but you may also see a sign change. And we see that, for instance, for rice in the tropics, that without adaptation, you see a decline in yield. With adaptation, you see an increase in yield. And the same is true for wheat in the temperate regions. Now, you rightly point out that the graph for maize in the tropics doesn't make any sense. That the assumption here is that farmers are so stupid that they're going to hurt themselves, right? Self-harm, essentially. You cannot really read this from the graph. The numbers that you see there are the number of studies. So this must be sample selection bias, right? That the sample with adaptation is different than the sample without adaptation. The closer we put this graph together. I've been described as like the most the most credible climate scientists in the world. I did not quite get it. This is a graph that comes straight out of the fifth assessment report, working group 2 of the Intergovernmental Panel on Climate Change, and the IPCC is known to employ people of doubtful statistical ability. So I think the explanation is that they're simply not comparing like this. But yeah, the overall tendency is clear. Crop yields may go up, may go down, and different crops in different places which fare differently depending on the scenario. That is not very insightful, I find. And I prefer to look at a slightly older graph from an earlier report of the IPCC, which integrates all these things into a model of agricultural trade. Essentially what happened here is that the modelers took these changes in crop yields and put them into models of how farmers make decisions, how local markets then respond to whatever is going on the farm, and then how international markets would respond. And of course also how consumers would respond to them. So in a sense, we're integrating everything, and there's an additional layer of adaptation that is added on top. That besides changes, 2 additional layers of adaptation that are added on top. Besides changes in, say, the harvest calendar, farmers may also decide to stop growing wheat and start growing maize. Maybe the sensible response to a warmer climate. Of course, you may also decide to shift the production of food away from one area to another through either national or international trade. All these adaptations are included as well. And then, of course, consumers may decide if wheat is in trouble, but maize is thriving, that we're going to shift away from, in Europe, from a wheat-based diet towards maize-based diet. So less pasta and more tortillas, for instance. Now, if you include all these things and you use a model like this, you can actually look at somewhat of a super indicator of what is actually going on with agriculture. And what we're looking at here is a retail price of food, and that's the consumer basket, as a function of the global mean surface air temperature. And what you see is that initially, at least in 3 of the 5 studies, the price of food goes down, which must mean that the supply of food has gone up. And then later on, it's the other way around, prices go up, so supply must come down. And then there's 2 studies that say that things are always bad. I put most trust in the green and the purple model by Darwin and Riley, who actually foresee that in the near future, for moderate warming, global agricultural production will expand. Part of that is just that different crops do differently under different climates, right? And that is just part of changing composition. There's one additional aspect that I haven't mentioned, and that goes back to the carbon cycle and back to what plants actually do. Plants photosynthesize, right? So they take CO2 out of the atmosphere, photosynthesis, and take water out of the ground mostly, and they combine the 2. They throw away the oxygen, which is good for us because we like to breathe oxygen, right? And then they keep the C of the CO2 and the H of the H2O and make it into a carbohydrate, and that's how they build their leaves and their stems and their roots and so on. And they need CO2 and water for plants. Or one way of visualizing CO2 or photosynthesis is that plants have little mouths on their leaves called stomata, with which they grab CO2 molecules from the atmosphere. And just like when you have a cold and you sleep with your mouth open, you wake up with a very dry mouth. That is because you evaporate a lot of water through your mouth. Same is true for plants. Their stomata evaporate a lot of water, or a lot of water escapes from the plant through their stomata. So if there's more CO2 in the atmosphere, they need to keep their stomata open for a shorter while to get the same amount of CO2 in. And that means they lose less water through transpiration, which implies that plants become more drought tolerant if there's more CO2 in the atmosphere. And that is actually a big part of the explanation why, at least in the short run, perhaps into the medium run, we would expect global agricultural production to increase as a result of climate change. And this particularly benefits those areas that are short on water, more found towards the poorer countries than in places like Europe. Right? So this is a particular boon to poorer countries. The reason that I paused earlier was I wondered, why is this sentence not there? Right? I was supposed to talk about. I talked about vegetation. Climate change also affects water resources, not just directly in terms of how much rain does fall, but obviously also if it gets warmer, you're going to sweat more and therefore you need to drink more. So the amount of drinking water changes, same true for plants, by the way. We drink a lot more water than we do. The demand for irrigation water will go up. Also, the demand for cooling water will go up. If you have a nuclear power plant, for instance, those things get very, very hot. So what we do is we put them near the river or near the sea. We take cold water from the river, pour it onto the plant so that it cools down, and then we pour the hot water back into the river. Right? Now, if the air temperature is higher, you need to cool harder. And if the river water's temperature is higher, cooling is less effective. So you will need a lot more cooling water to achieve the same amount of cooling. That may become a constraint on energy production. During recent heat waves, France, for instance, had to close down a number of nuclear power plants already, because otherwise they would run the risk of overheating. Now, the heat waves occur in summer. Peak demand for electricity in France is in winter, so they have an oversupply of electricity anyway, so there is not a big problem there. Those nuclear power plants were actually shut down not because of the inability to cool, but because it would be illegal to cool. Because of nature protection legislation, power plants are not allowed to put cooling water back into the river if it's too hot. It cannot be hotter than 32 degrees, otherwise you're not allowed to put it back into the river, and that is to protect local wildlife. And so you would fry the fish if you put in hotter water. Now, as I said, these things happen in summer, and in summer there's always a surplus of electricity in France. It's a bit unclear whether they would do the same thing if there was a shortage of electricity around that time. Essentially, then Jean-François Hollande would have to put his hand on telly and explain to the French that, yeah, he turned off the lights in Paris in order to save some pigs, which would not do good for his popularity, low as it is already, right? If it really would come down to the choice of sort of plunging Um, Plunging parrots into darkness or frying some fish. I think it's pretty obvious what they would choose, but at the moment they're turning off the nuclear power plants during heat waves because of restrictions on the temperature of the cooling water that is discharged back into the river. So there's all sorts of things going on there as well. And then to continue the story with water resources, there's droughts and floods. I spoke about that 2 weeks ago. This is a different graph. I now focus on the bottom map. In red, you're looking at those areas where flood frequencies would decrease. In blue, you're looking at those areas where flood frequencies would increase. So essentially, the same floods, the same amount of water would come down the river more often. And then, of course, you have to either cope with the increased flood frequency, or you would have to raise your dikes or whatever protection you're using, and that is, of course, costly. The reduction in flood frequency is not necessarily a good thing. Floods often put sediments in agricultural land, and that may be a problem. Reductions in flood frequency may also be an issue with transport. This may also be a symptom of there simply not being enough water in the river to send the ship across. Right? So it's not necessarily the case that a reduction in flood frequency, yes, would bring savings in terms of damage that you would avoid the costs of flood protection that you would avoid, but it may actually bring other negative consequences. And vice versa. Of course, more water in the river movement. So none of these things are necessarily simple or unambiguous. Continue the story. It gets warmer in winter, you need to heat your house less. If it gets warmer in summer, you need to spend more money on refrigeration and air conditioning. I talked about energy production already. Cooling water, thermal plants, as the name suggests, work on heat, and if things are hotter, they don't work as well. Same is true for electricity lines, by the way. It gets warmer, they get more resistant, and it's harder to transmit electricity under hotter conditions. Climate change obviously affects tourism. Large amounts of people, Europeans, Northern Europeans, spend their holidays in Spain. Not because they like the people so much, not because they like the food so much, not because they speak the language, but because the weather is better there, right? And it may be, perhaps not for Spain, but definitely for Greece, that the summer months will become too hot for us Northern Europeans to bear, right? And it may be that people in 50 years' time will have their holiday in Brighton rather than in Barcelona. Right? Brighton also is very beach is comparable to Barcelona, because the weather sucks, right? So you would see big changes in tourism as a result. Climate change, skiing is another obvious example. Climate change would also affect labor productivity by 30 to 40% in places such as Southeast Asia, at least according to one study. That is a drop in labor productivity. The reasons for that are the same as for some of the health intensive climate. So we are warm-blooded animals. That means that we need to keep our body at a constant temperature, 37 degrees. At the same time, there's all sorts of things going on inside your body. Your brain is doing things, right? Not necessarily what it's supposed to do, but it is doing things. Your heart is doing things, your lungs, your tummy, and so on. Actually, your body is working all the time, and all that activity generates heat. So if that were the end of the story, we would just heat up and our organs would all fail. So we have a cooling system as well. Um, and we simply lose a lot of heat through our skin. If it gets warmer, we start sweating. Essentially, we push little drops of water out and then they evaporate. That actually cools us down. Now, there's two aspects to that. One, as you know, if you work or if it's very warm outside and you try to go running or something, you get exhausted much more quickly than you just can't. And that also means for other forms of hard physical labor, it simply becomes more difficult if it gets hotter. And it's even more true if it becomes more humid, because then sweating becomes more difficult, because if the air around you is already 99% saturated with water, it's much more difficult to evaporate sweat, right? Because the sweat has nowhere to go. And that means that if some places that are already hot, already humid, get hotter and more humid still, then it becomes probably impossible to do farm work during daytime, during summer. And sweatshops would sort of do honor to their name. Now, those are effects on labor productivity. The same is true for heat stress and all the diseases that are related to it. As I said, your body has to work hard to keep yourself cool, and the hotter it gets, the harder it is to work. Now, for young people like you guys, young and healthy people like you guys, you just get a little bit tired during winter. They're very young, they're very old, people with respiratory problems, people with cardiovascular problems, their bodies simply may give in. Their hearts simply may not be able to keep up with all the additional stress that very hot and very humid weather poses. Right? You'll be like that one day too. So you would expect if there's more heat waves, if the planet is hotter, you would expect more heat waves. The atmosphere is warmer, it can contain more water, so it becomes more humid. You would expect more heat waves and more heat-related diseases. Same is actually true for, or the opposite is true for cold stress. We need to keep our body at a constant temperature. So if you throw us into a very cold environment, we're in trouble too. And most of us can cope, but cold puts stress on the body as well. And that particularly people with pre-existing cardiovascular problems may not be able to cope with this. And you would expect that if it gets warmer, you would see less cold-related diseases. Now, in a place like the Netherlands, the number of excess deaths is 10 to 100 times as high than the number of heat-related deaths. People tend to die in winter time. And you would expect, therefore, that climate change would have a net positive. Some of the winter, as some people say, most of the winter-related deaths have actually nothing to do with cold, but everything to do with behavior. In summer, we spend lots of times outdoors. The outdoors is much larger than the indoors, so we're further away from other people on average. Whereas in winter time, we're much closer to other people, and that means that infectious diseases have a much greater chance of spreading. And that explains a lot of the excess winter deaths. But this direct cold stress is not correct. Now, turning to infectious diseases, I talked about plants, I talked about animals. Some of these animals are actually positively dangerous for us. Mosquitoes bring all sorts of diseases, malaria, dengue, schisto. Other little critters bring other diseases. Most of it's names that you don't want to try to pronounce, right? These diseases will be different in the future as well. I'll be coming back to malaria tomorrow at length. If you leave your food out of the fridge, it spoils. If you leave your food out of the fridge on a hot summer day, it spoils faster. So you would expect that in a warmer environment, you would see more food poisonings. You would see more water-related issues, and so on and so forth. And then, last but not least, if seawaters get warmer, they expand. That leads to sea level rise. Sea level rise submerges land. Unless you spend money on protecting the coast. You would do that, say, along the Wadden Sea. Then you raise the dikes around the Wadden Sea, the water rises. The natural response for an area like the Wadden Sea would to migrate inland. If you raise the dikes on the coast, then they can't migrate inland, and that means that wetlands would drown rather than migrate. So you would see a net loss of coastal wetlands, and you would see saltwater increasing. A lot of people worry about what sea level rise would do to atoll islands. Small islands made of corals that are rarely more than 1 meter above, the highest point is rarely more than 1 meter above sea level rise, above sea level, and you would expect that by the end of the century, most of that would have disappeared under the sea. And these islands would have to be completely evacuated, and that would essentially bring an end to the existence of entire countries like Tuvalu. That is not true. Tuvalu will have to be abandoned long before it disappears under the sea, and that has everything to do with saltwater intrusions. These little islands, coral islands, have a bell of fresh groundwater under their feet. If sea level rises, the pressure of salt water on the freshwater increases. That means that more salt water will intrude into their groundwater reserves, and they will essentially lose their freshwater reserves long before the island disappears under the sea. The island disappearing is a prospect of 70, 80, 90 years, then losing their freshwater resources is a prospect of 30, 40 years. It will come much sooner. And yeah, if you have an island but no fresh water, then there's little point in you being there. This is true on small islands. It is also true across all the coast. So also in places like the Netherlands and in any coastal area, you would see an intrusion of brackish water into your groundwater, essentially making it useless for drinking water, making it useless for plants. Right? Talked a little bit about adaptation, but I'm going to drive the point home. What you're looking at is a picture of a beach. You probably figured that out. This woman here is lying on the beach, and it is probably only some 40 centimeters above the level of the sea. This is a very dangerous thing to do. I mean, if sea level were to rise by 1 meter, sea would drown. Millions of people would drown because of sea level rise. Right? Wrong. Completely and utterly wrong. Right? Why is this wrong? Well, most people spend a few hours on the beach only. You may come back the next day, but they have no reason to go lie in the same spot again. And if they see that for some reason the spot that is now nice dry sand has become water, they have even less reason to go lie and sunbathe on the same spot. Right? Moreover, right, so the beach population renews itself every 2 or 3 hours. A meter sea level rise is 80, 100 years in the future. Why would this woman come back in 80 years? Probably not even alive in 80 years. Why would her children and grandchildren insist on lying in the same spot sunbathing as grandmother? Right? People aren't dumb. Yet, you should have put it in. Yet, red studies that you're looking at, sorry, all assume essentially this. And this is the standard assumption in the climate change impact literature. That farmers keep doing the same thing. They keep planting the same crop at the same time, applying the same fertilizers, applying the same irrigation, even if they see their crop fail year after year after year after year, they keep doing the same thing because grandpa did it this way. Is that a realistic model of human behavior? No, not at all. It is a very simple model, a very simple way of modeling the effects of climate change, and that is why it's so attractive to academics. Like, you don't have to make an assumption about what those silly humans will be doing. You're making an implicit assumption. It's a sort of the default assumption that particularly natural scientists who study the impact of climate change stick in the models. It's complete nonsense. But that is unfortunately what most how we bring now the Deputy Administrator of the Energy Information Agency of the United States in order to illustrate to some geographers just how bloody stupid they are. It matters a great deal what you assume about adaptation. We're looking at here the impact of sea level rise. Sea level rise is on the horizontal axis. On the vertical axis, we're looking at the number of people flooded per year. And this is a bit of an ambiguous concept. People flooded includes people who get their toes wet, as well as people who are entirely submerged. So there's no indication of the intensity of the flooding. At least one body part of that. And then we're looking at three alternative scenarios of how the future might unfold, and three alternative assumptions about how coasts would be protected. So in the, let's focus on the red lines, doesn't matter, which is the one we pick. Let's focus on the red line. The solid line assumes that dikes and levees and groins and beach nourishment and what have you, and seawalls stay as they are now. And what you see is that if sea level would rise, then at the moment about 50 million people are flooded, 50 million people on the coast are flooded each year, and that would go up to 500 million or so. So that's a tenfold increase for a meter sea level. The dashed line makes a different assumption. It assumes not that dikes, etc., stay as they are, but rather the protection level offered by dikes stays as they are. It is in this area the nominal protection level against sea floods is 1 in 10,000 years. That is, if you were to sit in this spot for 10,000 years, you would expect it to be hit by a flood only once. The dashed line assumes that its protection standard stays the same in the future, whereas the solid line assumes that the dunes will stay the same. And you see that that actually makes a substantial difference to the impacts of sea level rise. Now the dotted line adds an additional assumption. If you travel across the world, say you would go to a coastal city like Lagos, you would find that it's not nearly as well protected against sea floods as Amsterdam. Because people there are a lot poorer and the government is a lot more chaotic. Now, in order to generate these scenarios of sea level rise, we need to have scenarios of greenhouse gas emissions. And in order to generate so much greenhouse gas emissions in the future, we need to assume that the people in Africa will be a good lot richer than they are today. So if we assume that the people in Africa are a good bit richer in the future than they are now, would we then also assume that they keep their protection standards against floods and all sorts of other things as they are now? That's very unlikely. So in the dotted scenario, we impose the condition that as people grow richer, they raise their protection standards. And for instance, Lagos would be as well protected as Lisbon is or as Athens is today. And that makes an even bigger difference. So instead of having 500 million people flooded each year, you would have only 50 million people flooded each year. And what you see is that actually, in this particular case, 1 meter of sea level rise raises the number of people flooded by an order of magnitude, but economic growth reduces it by an order of magnitude. And the number of people would stay at the number of people flooded would stay at 50 million per year if you put the two together. In fact, they exactly cancel here, almost exactly cancel, is happenstance, but we find often that economic growth is as important as sea level as climate change for the impact, if not more important.